How do large ships weighing several tons stay on the surface of the water while tiny pebbles sink to the bottom? In this video, we're going to explain how things float and why. The answer can be described by Archimedes' principle. Archimedes' principle states that a buoyancy force exists when an object is submerged in a fluid. The weight of the volume of water that the object displaces is equal to the force that the fluid applies upward on the object. Another way of saying this is that the buoyancy force applied by a fluid is equal to the specific weight of the fluid times the volume of the submerged part of the object. In this video, we use this toy submarine starting at the surface of the water and moving all the way to the bottom of the tank. This will allow us to show an example of this buoyancy force in action and why some things sink and others float. In this first part of the submarine's journey, it is filled with air and has a smaller specific weight than that of the water. It floats on the surface with only a small portion of the submarine submerged underwater. The submerged volume of the submarine multiplied by the specific weight of water is greater than that of the weight of the submarine. The specific weight of the submarine while it is floating is less than the specific weight of the water. The density of the submarine is less than that of the water. Since this is a submarine, we will now explain how it is able to dive under the water despite this buoyancy force pushing up on it. As the submarine begins to descend to the bottom of the tank, it begins to take on water. This will increase the density of the submarine as it replaces the air with water inside the hull. Therefore, the weight of the submarine will increase. So now, at the second stage of descent, the submarine is suspended within the water. At this point, the buoyancy force will be equal to the weight of the submarine, since the force pushing down on the submarine is equal to the force pushing up. Also, the density of the submarine is equal to the density of the water it is suspended in. In other words, the specific weight of the submarine is equal to that of the water. Now, in the third stage of descent, the submarine is resting on the bottom of the tank, and all the air within the hull of the submarine has been replaced with water. Now the specific weight of the submarine is greater than that of the water, and in effect, the weight of the submarine is greater than the buoyancy force. The specific weight of the submarine when at the bottom of the tank is 9.905 kilonewtons per meters cubed, and as mentioned above, this is greater than the specific weight of water, which is 9.807 kilonewtons per meters cubed. In summary, the buoyancy force is the difference between the forces pushing up on an object and the forces pushing down on an object. This is directly related to the specific weight of the surrounding fluid multiplied with the volume of the object. When the submarine was floating at the surface of the fluid, the force of buoyancy was greater than the weight of the submarine. When the submarine was suspended in water, the force of buoyancy was equal to the weight of the submarine. And when the submarine was resting on the bottom, the force of buoyancy was less than the weight of the submarine. The study of buoyancy force can be applied to many different applications, which include design of offshore oil rigs, boat design, submarine design, and any other application that involves suspending objects in fluid. Hopefully, following the conclusion of this presentation, any listeners have an enhanced understanding of the buoyancy force and Archimedes' principle and can apply it to their daily lives as an engineer.
Hush, little baby, don't say a word. Mama's gonna buy you a mockingbird.